we're going to be using Colab, Google Colab today, to run this notebook and workshop. If you never used Colab before, this will probably be a really useful resource for you. So basically, what Colab is great for, it's not only great for running code in the browser, but also it's really good for having GPU access. So, for example, for this workshop, we're going to be using a GPU to speed up the training of our neural network, because neural networks run a lot faster on GPUs simply because the amount of linear algebra that's going on. So yeah, I'm going to go ahead and send the link in for this notebook. So basically, there's kind of two ways you could participate in this workshop. Either you could just watch and you could just watch the tutorial, and that's fine. You know, if you're in bed or something, you don't really want to, you probably could run this whole thing in bed. It's actually not too bad, but you know, if you're not bothered running it yourself, you can just watch, and that would just be pretty useful too. So like all the code here is fully working already. So we'll be running through each of the cells one by one, explaining what's going on. And so yeah, if you want to open up Colab, luckily enough, being in Trinity, we all have Google accounts. So you can just use Colab with your Trinity account and just go straight into it pretty much. So like, all right, I'll just show you kind of the very basics of using Colab now. So to check what kind of runtime you're working with, well, you might see, I'll actually restart everything here just so we're all starting from the same point. So you'll probably see like a connect button here. If you want to make sure you're using a GPU, you can go to change runtime type. I'm pretty sure it should be GPU by default, just by the way this notebook is set up. But yeah, that's a good way to always check using the GPU. And so Colab is completely free. So you don't always want to be on the GPU the whole time, because there's rate limiting because it's free. They don't want people just hogging the GPU when they're not using it. So, you know, at any point in this tutorial, if you get a warning about not using the GPU yet or something, don't worry about it. You're not going to get charged or anything. The worst that would happen is just them switching you to a CPU runtime instead. So yeah, the way Colab works, you can have Markdown or you can write code too. So actually what we'll do straight away, if people have the notebook running, go ahead and run the first section. So installs and imports, this will take a few minutes. So we'll go ahead and run that straight away. This will just be, it was quick for me because I already have installed this stuff before. For you, it might take a few minutes. So basically, this section is just installing PyTorch. So we have a few installs of PyTorch and some helper functions. We clone in another repo that has a few helper functions in it. And then we import the various libraries we're going to be using in this tutorial. And so as well, this notebook was adapted from another notebook on object detection. And we have changed it so that we can use a different data set and cleaned up all sorts of different stuff and stuff like that. Just to give credit to that person, if you want to go to their notebook, it's here. Okay, so you may still have this running. That's no problem. I'll go ahead and talk a little bit about data sets. So like a huge part of all machine learning and AI is data sets. So like you can have a really good idea about like an AI company you want to make or a problem AI could solve. But if you don't have the data to train your model, it's no good to you. You know, you really need data. So like, for example, you know, this problem we're working on, make a cone detector. If you want to make a cone detector, you need to find the data first. So that's the first thing we had to do. So I'll give a couple of quick tips on finding data sets. So like there's a couple of things you'll often run into when you're trying to find data sets. because you'll be looking through old code, old blog posts, and one huge thing would be like broken links. So like somebody would have a link to some cloud storage they'd previously been storing a data set on, and then they don't pay for it anymore, so it's gone. You can have people who claim to have open source data sets, but if you want access to them, you actually have to contribute. And then so yeah, I'll give you a couple of kind of hacks for searching for data sets. So like, for example, in this one, one really good thing, I think the way we actually ended up finding it is I would look up like cone detection, PyTorch, and then one thing that's really handy if you've never seen, you can search particular websites on Google. So I'd say cone detection, PyTorch, site github.com, and this will give me all of the repos, or anytime someone has posted something on GitHub to do a cone detection. So then rather than searching for the data set, if you actually search for the code that you know needed a data set, that can be a really good way to actually find one. So that's actually what we ended up doing. And so yeah, like we were just scouring GitHub repos to try to find somewhere, and that's actually what we ended up doing. So if you want to take a look, we just basically found a Dropbox link to a data set with 123 annotated images. So yeah, I'll go ahead and download this data set then, and we'll have a look at what's in it. So yeah, just download. So like Colab notebooks, they're run on a Linux runtime. So using standard Linux commands like wget and unrar, basically unzip, all of those commands you can use, and you can see your file system here. It has a file system. So basically, oh yeah, I'd already actually downloaded this, so I already have it. I don't need to worry about this one. So then basically what this data set was then is it pulled in one folder containing training data and one folder for test data. So this is standard practice in machine learning and AI. You will have your training data and your test data. And the reason for that is, if you like, it's good to use all the data you can, and that would theoretically be, that would train your model the best if you use all the data you have. But the thing is, if you've used all the data you have, how are you going to predict that it works? You need data to actually check that it has worked. So you'll usually have one training set and one test set. So basically you'll use the training set to train your model, and then once you've trained the model, you'll use stuff from your test set, basically just to double check that it works. So let's have a look at what's in the training set. So we can go over here, we can click on any of these and it'll pull up the file on the right side, and we can have a look. So yeah, basically it's all just different images of cones. And as you can see on the left, for each image, there's also a text file. So if we take a look at this image, it's got one cone in it. If we take a look at the text file, it's got these numbers here. So what do these stand for? So 0 is the label. So we're only looking to detect cones. We could theoretically detect all sorts of different objects. So you could have a label for each of them. We only have one, so it's fine just to label it 0. And then we have the center X coordinate. So that would be like here. So it's just the X value of the center. And we're talking about the center of the cone here. So as you can see, the cone was actually perfectly in the center here. And then we've the Y value of the center of the cone. And then we have the width of the cone and the height of the cone. So basically what we have is all the information we need to draw a box around the cone, because that's what we're aiming to do here. We're aiming to see all the cones in the image and draw boxes around all of them. That's what we want our model to be able to do. So yeah, if you want to train a neural network to do this, then you need the data. So the data for us is an image and the corresponding positions of a box around the cones in that image. So if so some of these will have multiple cones in them, so there will be multiple rows of coordinates. Okay, so next then, so yeah, some PyTorch stuff. So basically, in this section here, we are making a dataset class which has a get item function and a length function. So, you know, this is kind of one of the big pieces you'll have to do if you want to use different data sets with different neural network models. You'll need to have a way of parsing the data and, you know, kind of just making sure it's in the right format so that it can be read by the network. So yeah, in this case, we make a cone images data set, and it extends the data set object provided by PyTorch. And the important functions here are get item and just length. So basically, the get item function then will so we know we have the path to our training set and our test set. So the get item function, it'll take in a path to one of the directories, and then basically what's going on here in get item is it will go through each of those images. So all the images that have a JPEG file ending, it will read them in, and it will read in the corresponding annotations from the coordinates of where they all are. So yeah, this is all, you know, it's just kind of muck work really. You know, you're trying to make sure that everything's lined up properly, that it is a good part of the process really, because to do that you need to completely understand your data set, or you at least gain that understanding by the end of it. So we'll go ahead and run this. And yeah, so just at the end here, then we pull in our training data set, and we'll just check how many images are in it. So we got 122, not a huge amount. And we'll see later that we're still able to train a model with just 122. But, you know, companies like Tesla and Comma AI, they'll have millions and millions and millions of images, because they have, you know, literally millions of miles of driving data of cars on real roads. But for us, we just have 122 images and we're still going to make it work. So yeah, all the images, another part is, you know, when you're parsing in the images, if you're feeding them to a neural network, they all got to be the same shape. So that's another thing we do. We just scale them and stuff like that. And then here's an example of the labels. So we've parsed those coordinates and we've parsed them into the various pieces. So yeah, as you go along, as we're running the cells in this notebook, you can either, you know, hit this run button, or what I'll do is I'll press Shift and Enter, and that will run and take you to the next cell. Okay, so now that we've seen our data set a little bit, let's visualize it properly. So we've seen, you know, we're trying to draw a box around the image, and we want to make sure that the boxes we have are lined up properly. So I'll go ahead and yeah, so we basically define a little function that just draws a width around the box. Sorry, draws a box with around the cone in the image, well, around the, you know, the labels that have been given, and this is the result. So this is just something from our training set, but it's good to have that visualization, because, you know, we can read the coordinates all we want and, you know, kind of line them up in our head, but it's very essential to know that the data you're putting into your neural network is correct, because otherwise, you know, the network will learn the incorrect thing to do. And it also helps with afterwards to make sure that it worked on the other end. So yeah, so this is an example of one of the images. So a bunch of cones, and they all have rectangles drawn around them. So like, when it comes to actually labeling these data sets, like you can imagine, okay, we have the data, but who's labeling it? Like Tesla actually have a massive labeling pipeline. So they'll have people manually labeling stuff, and there's companies set up just to solely do this labeling. And I've done it myself. It's super tedious at times, but if you're ever looking for kind of a labeling tool, label image, label img is kind of the standard. So like if you were to make your own object detection model on something, we're doing one for cones right now, and we're only using 120 images. You could take this notebook and use something else. I'd ideally recommend like a minimum of 200, to be honest. From my experience, you'd kind of want at least 200 images to get something working well. But yeah, like you literally go through and you would use a tool like this to draw boxes one by one. So you might want to have a few podcasts lined up before you start that thing. So yeah, let's go on to the next bit. So more data stuff. So we've only got 120 images. So that's not a great amount, but there's more stuff we can do to kind of get more data. So like it won't be perfectly new data, but it's enough so that it's new enough, which will help our network learn. So what I mean by this is we'll do augmentations to the data we have so that we can get more. So like what we do this time is we'll take all the images we have and we'll keep those, but we'll also make a flipped version. So then if you think about it, then you've got double the amount of images, except because like the neural network doesn't know that they're perfectly symmetrical now. It just sees another image that has cones in it, and that's still useful. It's not a perfectly different image because they're still going to have similar backgrounds and stuff, but it's better than nothing. So yeah, we set up some transforms so that as the inputs are being passed in to the neural network, it'll also flip them and use that as well. So then just a small little bit more PyTorch stuff. So we have our data set now, and what we'll actually do is set up data loaders. And what these do is they pass everything into the neural network. And the reason we have a specific thing to do that is because there's a bunch of stuff we can set up so that it's all passed in correctly. So for example, one of these things is, so we talked about having a training and a test set earlier. Within the training set, what's pretty much always done in AI and machine learning is there will be a training and validation. So the neural network, so as we're training the network, we'll also look at a validation set. So we're training, the neural network is only ever training using the training set. So what we'll actually do, sorry about saying training set so many times, but basically we take the training set and we only use 80% of it to actually train the network. And then the remaining 20%, while we're training, we'll kind of look at that, how the accuracy on the 20% is increasing, because that gives us a good idea of how much better our neural network is getting at predicting the cones as we do more iterations of the training. So yeah, here we select a train test split of 20%. So 20% of our data in our training set will be used to validate how the neural network is doing, and the other 80% will be used to actually do the training itself. So now that we're moving on to the specifics of the model, I'm actually going to pass you on to Harvey now. So Harvey, if you want to switch over, I'll stop sharing my screen now.
Yep, I will share my screen just now. So I think that's working. Can you see the notebook?
Yep.
Yeah. Okay. So I'm Harvey, and I'm on the Formula Trinity autonomous team, and I'm just going to talk a bit about the model and actually training it. So I'm going to start a training first because training takes a bit. This model is nice and small, so it only takes around 3 minutes, but I'm still going to run the code and then we'll go into a bit more depth. So the first thing here we're doing is we're actually loading the model. And you might notice the word pre-trained is used a lot here. So what that means is we take a model that was already trained to do something like detect people in a picture. And all we're doing is we're taking that model and we're saying we're not doing that anymore. Now we're detecting cones and we train it from there. It just gives us a bit of a head start since it doesn't have to learn from scratch how to perceive images and stuff. So we'll run that. And this was actually trained on something called the COCO dataset, and that was made by Microsoft. And it's just object detection for a load of random stuff, but it's really big. So it lets it learn a lot of stuff in advance. And then we prepare it. We prepare the optimizer and a few what's called hyperparameters like learning rate. And I'll go over them a little bit in a second. But we prepare it for training and it just gets everything ready. You can see there I've downloaded from the internet the pre-trained weights. And yeah, that should it's a bit slower, but it's done now and we can start training it. And in AI, you'll see the word epoch used a lot. Epoch just refers to one whole training run over the set. So it runs and it trains on the data set, but typically you do that over and over to make it get better and better. So we're going to do it for 5 times here. So start that training and you'll see it start to run. And just while it's doing that, I'm going to talk a little bit about how neural networks work in general, and then specifically how object detection ones work. So this is a really simple neural network, and our one is much bigger than this, but it's nice just to sort of illustrate it. So the neural network is made up of layers, and the first one is the input layer. So basically every value in a green circle here is an input, and sort of in R1, each value is like a pixel from the picture going in. And then what we do is we have a vector of numbers and we call them weights. So for example, you can see the hidden layer here, the first green circle, it has inside it essentially a list of numbers and each one's a weight. And what we do is every single input value from the layer before is multiplied by a corresponding weight. And then all of those weights multiplied with the input values are added together. And finally, we add just a constant that's called a bias. And that gives us some output. So you can see in this little black box up here, the calculation for the first green circle. And each of those green circles is called a neuron. So you can see it multiplied 2 by the first weight, which was 0.1, and so on. And we got 3.3. If you're familiar with statistics, you might be going, hey, that looks like a linear regressor. And that's because it is. A neural network is like lots of them stacked on top of each other. But we actually don't want it to be linear. There's a good few reasons why that's not ideal. So what we do then is we just pass it through some kind of nonlinear function, and that just takes it in and transforms it somehow. And we do that over and over. So every single green circle here is a neuron, and it has its own set of weights, and it multiplies the entire layer before it by those weights to get its own value. So going back to the statistics thing again, it's like a load of linear regressors working in parallel. And we do that over and over, and we call all of them together a layer. And here we only have one hidden layer. Typically, you'd have many more. But basically, we'll go on to the next layer, which in our case is the output layer. And it works the exact same way, except instead of the weights being multiplied with the inputs, they're multiplied with the values of the layer before it. So it's as if for this layer, the input is the layer before it. It does the same thing again, except this time we add some kind of meaning to the output. So you can see here, the first one had a value of 0.93 and the second one 0.62. So if we were, say, training this to be a classifier that says if something is a cat or a dog, what we do is we'd say this is the probability. So 93 is 90%, 93% probability that it's a cat and 62% that it's a dog. So you might be wondering where these weights come from, because they are these magical numbers that work perfectly to get us the output. And at first they're random. we just choose some random numbers, and that means that we're just multiplying things by random numbers, so the output is random. But what we do is we have something called a loss function, and all that does is measure how bad our thing is performing. So for our one with the cones, it just measures how many of the cones are detected and if the box is in the right place. And so now what we have is we have a single number, and the higher that number is, the worse our neural network is performing. And we want to just lower that. And one really nice way to do that is calculus. And so what we've done is we've kept all of these operations differentiable, which means that we can just do a lot of very complicated multivariable calculus, and we can work out what direction to shift all the weights in order to minimize the loss function. And that sounds very complicated, and it is. There's no way I could do that by hand. Originally, I think they did a few times just testing, like back in the 60s. But these days, all the frameworks have something great called AutoDiff built in, and it just does all that for you. So you don't really have to worry about it, but it is good to know how it works underneath, because it lets you kind of design new improvements and know when things go wrong. So like I said, this was a very small one. Object detection ones look something more like this. And in this case, each box represents a group of layers. So I think there's something like 50 layers in this, and they get very, very big. But it's the same thing underneath. There's some differences in how the layers connect to each other, but yeah, underneath it still works on those basic principles that I described before. And in fact, this isn't actually the model that we're using, but it's the current state of the art, and it's the one we were going to use. It's just the last minute we changed, but they're both good. The way this one works, just to give a bit of background from what I said a minute ago, is instead of predicting, in my example, I said it would predict a probability of being like a cat or a dog. This one predicts, are there boxes? What size are the boxes? And then it also predicts, like, for every square of the image, we divide the image up into squares. We like work out for that square, what are the probabilities of it being, and in this case, it's dogs and bicycles and cars. In our case, it's cones. So it is like a classifier here. It's just, it's a classifier on loads of little squares of the image. And then for each square, it also predicts, is there a bounding box here? And you can see that we end up with a huge number of bounding boxes. But with a few tricks, we can get it down to just the highest probability ones. So if I go back to our code now, it looks like we have finished training. So this step here is what I mentioned a minute ago, and it's called non-max suppression. And what that does is it looks at overlapping bounding boxes, and it just tries to merge them together. And then anything that it's not very confident in, so if it said there's a box here, but only with 20% probability, we just throw it away. So we run that here. And finally, we can take an image from the test set. So David mentioned this earlier. Basically, it trained on a load of data, and a common problem is that it can start to memorize that data. So it could just spit back out to us exactly what it saw. And that's not very good, because that means if we put it in an actual car, it won't be able to work because it'll be seeing new things it hasn't memorized. So we keep some data so that we can run it and see how well does it work on new data. And you can see it worked pretty well here. It did put boxes around the cones. And just a reminder, unlike the picture you saw earlier, these aren't boxes from our data set. These are boxes predicted by the neural network. But yeah, so that's kind of it for this. I just wanted to mention, I know I rushed through that very quickly here. They are very complicated and it's very hard to explain. I definitely didn't understand neural networks the first time I heard about them. So what I would recommend, if you are interested in this, are these two courses. I'll send the link in the chat in a minute. They're both quite good. Machine Learning by Stanford is a good one. It gives a load of background on sort of a lot of traditional machine learning methods. It's very nice if you want to build up like a good, strong background in it. But if your goal is just to get to the state-of-the-art cool stuff as fast as possible, this one here, Deep Learning Specialization, is nice. They are both a little pricey. They're paid, but they're very worth it. And they also give you a certificate, which look quite nice to put in a CV. So yeah, that's it from me. you.